Guys, assalamu alaikum. So let's solve this question number 16. This is a magnetic field question from the year May 2023. We will solve this question in a very detailed way, and we will probe into this question so that we can answer this kind of questions which are really repetitive in your exam session, so that you guys can answer this question very easily. So let's solve it. In the question they have said a search coil is used to investigate magnetic field. Okay, there is a coil which has been used, and this is a search coil. The search coil consists of a coil of thin wire connected to output terminal as shown. So the copper wires of this coil is connected to these output terminals. This is a search coil which has been used to investigate magnetic field. Okay, so let's complete what they have written us to do. So if we probe into this question, they have said a student placed the coil in a magnetic field with the x-axis parallel to the direction of the field. Okay, so the direction of the field is in this position. This is the direction of the field. And as the direction of the field is downward, the axis of the coil is also downward. So the axis of the coil, actually the magnetic field of the coil is also downward, and the direction of the magnetic field is also downward. So they are parallel. They are parallel at the moment. But the coil was rotated through 90 degrees. So when the coil was rotated, the axis of the coil is now in this position. You can also say it as the magnetic field of the coil is perpendicular. The magnetic field of the coil is perpendicular to the direction of the magnetic field of the terminal. Okay, so they are now perpendicular. So they are now perpendicular, and it was parallel before. So what is the change here? So let's go and have a look at it. They have said as the coil was rotated, when the coil was rotated to perpendicular, when the coil became horizontal, it was vertical before, a potential difference was detected across the terminal. So when they have said a potential difference was detected by the movement of the coil, when the coil was rotated, so the coil was moved. When the coil was moved in a magnetic field, a potential difference was detected. It gives you a hint that there is a change in magnetic flux linkage which induces an EMF, and that induced EMF was the reason why the potential difference was detected. So let's go and write it down in our own words. The thing is, there is a change in magnetic flux linkage which induces an EMF. As the coil was moved in the magnetic field of the terminals, there was a change in magnetic flux linkage. It was rotated. That means it was moved, or it was perpendicular to the direction of the magnetic field. So we have answered this question very easily. In this year, May 2023, the question was really easy. That's why more or less everyone got 2 marks in this question. But it's not certain that it will be that easy in your exam paper as well. So I'm going to make you guys understand this difficult topic using my own notes, so that you guys can solve it when it arrives in your exam day. So let's go and solve it down right here. In this question, if you see, I have written down one thing. This is the direction of the coil, and this is the direction of the permanent magnet. This is the direction of the permanent magnet. This is the direction of the permanent magnet. So we all know this is the direction of the coil, this is the direction of the coil, this is the direction of the coil, and this is the direction of the coil. Okay, so you all know EMF is equals to d and phi divided by time. This is what is the flux linkage. This is our flux linkage. So we can say EMF is equals to flux linkage divided by time. This can be said, right? So it can also be said that if the flux linkage divided by time, this is a flux linkage by time graph. So the gradient means flux linkage divided by time. So the gradient of flux linkage time graph, the gradient of this flux linkage time graph gives us the EMF. So when the flux linkage is at maximum, When the flux linkage is at maximum, the EMF is 0. When the flux linkage is at 0, the EMF is at maximum. So what is the reason behind that? The reason behind that is that when the flux linkage is at maximum, it is a horizontal line. The gradient is 0. So the induced EMF is 0. But when the flux linkage is here, when the flux linkage is 0, the gradient of the flux linkage is maximum. So the EMF is maximum. Here as well, the gradient is 0. So the EMF is 0. Here the gradient of the flux linkage time graph is maximum. So here the EMF is also maximum. But here the EMF is 0 because the gradient of the flux linkage time here is 0. So we have compared the flux linkage by time graph with the EMF time graph at the moment. So let's go and look at this period here. When the coil is perpendicular to the direction of the magnetic field, when the coil is perpendicular, the flux linkage is maximum. When the coil is perpendicular, the flux linkage is maximum. But when the coil is parallel to the magnetic field, the flux linkage is 0, but the EMF is maximum. When the coil is again perpendicular to the magnetic field, it is also again maximum, but the flux linkage is maximum, but the EMF is 0. So looking at these graphs, we have understood these simple topics which are really important, and it may come in your exam day as well. So let's go. It was an exam question as well, so let's go and look at one exam question. This is the exam question which came in recent years. So let's go and look at it. They have said, explain why the EMF varies between maximum and minimum. This is the maximum and this is the minimum. So why does the EMF varies between maximum? We can answer this question in this way. This was a 4 marks question, so let's go and write it down. You can also memorize it by understanding. After understanding, you can memorize it because it may come in your exam day as well. So let's look at it. Induced EMF is equal to the rate of change of flux linkage. Induced EMF is equals to the rate of change of flux linkage, which we know as EMF is equals to flux linkage divided by time. So EMF is equals to rate of change of flux linkage, which means flux linkage divided by time. Maximum EMF is when the coil is horizontal. When the coil is horizontal, we have looked at it. When the coil is horizontal at this position, when the coil is horizontal, the EMF is maximum, but the flux linkage is minimum. Here is written maximum EMF when the coil is horizontal. When the coil is horizontal, the flux linkage is 0, but the EMF is maximum. So any movement will lead to a large change in flux linkage. When the EMF, when the flux linkage is 0, suppose you have 10 taka and I am giving you 100 taka. So this will make you a lot happier because you just had 10 taka and I am giving you 100 taka. So there will be a greater change in your mindset. You have gone now from 10 taka to 110 taka. And if anyone has 1 crore and I give him same 100 taka, it will not matter to him because he already had 1 crore and this 100 taka doesn't matter to him. This is the same right here. When the flux linkage was 0, the EMF was maximum. But if there is a small change, in the flux linkage, if there is a small change, then that will lead to a large change in the flux linkage. Okay. But when the coil is vertical, the flux linkage is maximum, and slight movement of the coil, if the movement is slightly moved, it will have a very little change like this. If you already have 1 crore taka, if I give a slight change or slightly move 100 taka more to your pocket, then it will not matter to you because you already have 1 crore taka. This is the way this should be answered, that if someone has the flux linkage 0 and the coil is moved even in a slightest way, then that will lead to a large change in flux linkage. But if the coil is vertical, the EMF is 0, but the flux linkage is maximum, a slight movement of the coil will lead to a very little change. A slight movement will not make a very big change, but here a slight movement will make a huge change in the flux linkage. So this is a very important thing. You can also take a screenshot of this page so that you guys can practice or even remember it before your exam day. You can also take a screenshot of this page as well. Okay, so let's move forward and answer this question again. So in this question, here it was parallel. When the when both the things were parallel, when both of them were parallel, just like this, when both of them are parallel, right here you can say, when the coil and the magnetic field is parallel, when the coil and the magnetic field is parallel, the flux linkage is 0, but there is a maximum EMF. So the same is happening here. This induces an EMF. So yeah, the things that I have make you understand in the last 4 or 5 minutes is not necessary for question number 16, but it is really necessary for different types of question which may arrive in your exam day. You never know. So let's go and let's move forward and solve question number B. In the question number B, they have said, show that the initial value of magnetic flux in the coil is this. So they have find out the magnetic flux. So we all know the formula of magnetic flux density is magnetic flux per unit area, which is B is equals to this by A. So we have been asked to find out this magnetic flux. So we know this magnetic flux density. This is our magnetic flux density. We just need to find out the area. We know the area is equals to, as this is a coil which is circular, so we can say area is equals to pi into r square, and we have got the diameter, so 25 by 2, this is our r, this will be square. So we can find out the area right here. So the area will be, if we use a little bit of calculator here, okay, so this 25 needs to be converted into meter, so I have to do into 10 to the power minus 3. Maybe it's minus 3. Just have a look at it, just 1 minute. V is equals to 5 by A. 5 is equals to B into A. Area is equals to 0.025 divided by 2 square into pi. This is our pi r square. So the answer will be 4.9 into 10 to the power minus 4. You can get it down here, 4.9 into 10 to the power minus 4 into this magnetic flux density, which was 0.18. So the answer will be 8.84 into 10 to the power minus 5 Weber. This is our answer. So we are done with question number B. I hope you guys have understood question B. Now let's move forward and answer question number C. In the question number C, they have said the graph shows the magnetic flux in the coil. Okay, the graph shows the magnetic flux in the coil while the coil was being rotated. They have given us the magnetic flux and the time, and they have asked us to find out the maximum PD. So here is where the things that I make you understood will come into its account. So let's see. They find out the maximum EMF. So maximum EMF. See, all know when does the maximum EMF comes. Here we know magnetic flux divided by time gives us EMF. So here the magnetic flux is, the gradient is 0. Here the gradient of the magnetic flux divided by time is 0. Of the magnetic flux time graph, the gradient of the magnetic flux time graph is 0. Here the EMF will be 0. But right here in this position, it has a wait a minute, it's difficult to draw with this. So this is the position so this is the position where the EMF is maximum because the gradient is maximum right here. So if we find out the gradient, we can also find out, we all know the formula of EMF. The formula of EMF is minus d phi by time into n. So we found out the number of turns as coil as 5000. We have to just find out this, which is the gradient of this magnetic flux by time graph. So if we find out the gradient here, we can say it's 0. We can say in this position it's 0.3 and 0, and in this position, if we take this position as well, it's we can take it down to 0. We can take it down as this is 8 and this is 0.15. Okay, so we can take it down as 0.15 into 8. So if we go and find it down, we can say, we know this is x1, this is x2, and this is y1, and this is y2. We know the formula of the gradient, y2 minus y1, x2 minus x1. So we can write it down 0.0 minus 8 divided by 0.30 minus 0.15. 0.15. So if we find it out into this 5000, which will be equal to 2.33, we can write the answer as 2.3. As the answers were given in 2 decimals, so we can write it down as 2.3. So let's move forward and answer the question number D right now. And the question number D, they have said okay, so now we can solve the question number D. So the question number D will be a little bit it has a lot of layers actually. We can solve this question. In the question they have said the output terminals of the coil are connected together. Okay, when the coil is in the magnetic field, here it is given the magnetic field. When the coil is in the magnetic field, the diagram shows a cross section through 1 turns of the coil. X is on one side of the coil. So this is the X and it is in the one side of the coil. The coil is rotated clockwise in the magnetic field, causing a current in the coil. Okay, so when the coil is moved, if a coil is moved in a magnetic field, it will induce an EMF. This EMF will drive a current. This EMF will drive a current in the coil. So is moved clockwise. The coil is moved clockwise. So the coil has been moved in this direction. So the force is on the right. The force is on the right. The coil is moved in the clockwise direction. The student states that the current at X is into the page. So the current here is into the page. So deduce whether the student's statement is correct. You should refer to Lenz's law. So we have to use Fleming's left hand rule. As they have mentioned Lenz's law, we have to use Fleming's left hand rule. So let's have a look at it. If we look at it more closely, we can see that we all know that creation opposes the creator. Okay, so the creation opposes the creator. So the coil was moved in the right direction. So when the coil was moved, there was a change in magnetic flux linkage, and that magnetic flux linkage induced an EMF, and that induced EMF drives the current. And when there was a change in magnetic flux linkage and EMF is induced, this EMF drives the current through the coil. This EMF drives the current through the coil. According to Lenz's law, the current which was driven in the coil will produce a magnetic field. This coil will also produce a magnetic field. The current on this coil will produce a magnetic field. This magnetic field will oppose the motion of the coil. So that magnetic field opposes the motion of the coil. So the coil was moving in the right direction. So the opposite force which will be created by the coil will be in the right direction, because the creation opposes the creator. I am making you guys understand again. There was a change in magnetic flux linkage because the coil was moved in the magnetic field. When there was a change in magnetic flux linkage, that induced an EMF. That induced EMF drives the current in the coil. That current produces a magnetic field. That magnetic field produces a force in the opposite direction. To oppose the motion of the coil. So the force is in this position, and the magnetic field, if you erase all the other things, as we has written this to make you guys understand. Now just keep it up to this and have a good at it. So this is the magnetic field, this is the force, this is the magnetic field. So we can conclude that the current was into the page. If you use your Fleming's left hand rule and put your force in this position and the magnetic field on this position, we can see that our second finger or our middle finger will be into the page. So we can conclude from the magnetic flux linkage that this is correct. So let's go and write it down in our own words. We can say by Lenz's law, current produced or induced, we can say produced, is so as to oppose the cause of the current. We said the creation opposes the creator. This is our point number 1. So let's go and write the point number 2, which will be force on wire due to interaction of induced current and field. There will be a force on the wire due to the interaction of the induced current and field on the opposite direction. So the force will be on to the left. So the force will be on the left. So by Fleming's left hand rule, current is into the page and the student is correct. To give you guys one repetition again, we have said by Lenz's law, the current produced is so as to oppose the cause of the motion. We have read it right here that this was the previous direction in which the force was given, and this is the opposite direction to oppose the motion of the to oppose the motion of the coil. So by Lenz's law, current produced is so as to oppose the cause of the current. Force on wire due to interaction of the induced current and field. So the force will be on the left. So the force will be on the left because the previous force was on the clockwise movement and which was in the right. But the opposite force will be on the left. So opposite force will be on the left. So by Fleming-Septon rule, current is into the page and the student is correct. This part is only on one of the part which you have to find out by yourself because I cannot show it on the screen. As you are grown up guys, you are now studying in A2 physics, so you have to be able to find out this, why the force is into the, why the current is into the page if the force is in this position, the magnetic field is in this position. Okay, so have a good day guys. We are done with question number 16. Though I have made this video very lengthy to make you guys understand a lot of different topics rather than the only question paper, I will solve all the question papers using this method so that you guys can understand all the topics more firmly and profoundly. And if you guys enjoy my video, kindly join my A2 physics high impact crash course and crash course batches for October 24, Jan 25 and May 25 candidates. Have a good day guys. We also have a BUET teacher from who has been teaching physics from a very long time, and he's an experienced teacher from BUET. He's studying in BUET and also giving P3, P4 and M1 S1 class in our coaching, in our online platform Edexcel Exam Essential. So you can join our channel as well in order to study maths, ASA2 maths under a very good teacher who is from BUET. Have a good day guys.